Hi there. Today I'd like to talk about one approach for using large language models responsibly in healthcare. Everybody is talking about generative AI and large language models and how they're going to revolutionize so many aspects of our lives. In those conversations, healthcare always rises to the top of the list. And there's good reason for that. Understanding healthcare is challenging. It's full of jargon and often hidden in opaque standards and tricky notation. Generative AI has the potential to cut through all that and make healthcare understandable. There are, however, just a few problems. First, when we answer questions in healthcare, it is important that we have the most up to date information we can. Telling Bob to make lifestyle changes based on a weight from 2 years ago is problematic, especially when Bob's worked so hard to make changes already. Having Bob repeat blood tests that he did a week ago is a waste of time and money. But even worse, prescribing Bob a new medication when we don't know what he's currently taking can be very dangerous. Having the LLM work off of stale data often leads to frustration and can lead to dangerous situations. But LLMs, after all, only know about the data they were trained on, and constantly retraining them is costly and time prohibitive. Also, LLMs are notorious for leaking their training data. Every day, we learn about new techniques for getting LLMs to share things they shouldn't. And people are understandably concerned about having their personal health information used to train LLMs. They're concerned the data will be exposed and will be used for purposes they don't even know. These are real concerns, and the complexities of LLMs makes it very hard to guard against them. Luckily, there are new techniques coming out every day, and one called Retrieval Augmented Generation, or RAG, can help us get around some of these problems. So let's chat a bit about how RAG works. To understand how RAG works, we first need to understand a concept called embedding. This is the process of assigning numbers to words. But we don't just want to assign random numbers. What we want is for the numbers that represent similar words to get grouped close together. We do this by training an embedding model. Over time, as we train the model with more and more text, it learns to give words that are similar in meaning similar numbers. Using our embedding model, we can take curated data and put it into what we call a vector index. Curated data just means data that we have reason to believe is true. It could be peer-reviewed articles from medical journals, or doctor's notes from a physical, or even information about how fast things go. Let's see how we can turn this curated data into numbers. Using our embedding model, we assign numbers to the words in the statements. We can now associate all those statements with numbers in our vector index. Next, we get a question we want to answer. We put that question through the same embedding and turn it into a numeric representation. We can then use that numeric representation to find the data in our index that is relevant to the question. This works like, let's say our question is, what is the fastest animal? Use the same embedding model to turn that question into numbers. We can then look for similar numbers in our vector index to find the curated data that is most associated with that question. We can then send that data plus the question to the large language model. The LLM can then generate a human-readable response to the question. So, given the data and the question, the LLM can give us an answer. This answers our two challenges nicely. First, it's much easier to update the index as data changes than it is to retrain the model. Anytime we get new information about Bob's health or how fast animals go, we can put that into the vector index and retrieve it easily. This means that we're always answering the question with the most up-to-date data we can. It is also much easier to implement security on a vector index. For example, We can remember which data we put in that has to do with Bob, and then only Bob's doctor can retrieve that data. Another doctor can ask the LLM about Bob all they want, but it will never divulge its private information because the LLM doesn't know. Only the vector index does. There are three things we need to consider when submitting the curated data to the embedder. The first is that patient health records include a lot of data. LLMs can only handle a small amount of data at a time. If we try to feed the entire record to the large language model, it won't do a good job of answering our question because it will either truncate the data or be overwhelmed by the useless facts. This is where FHIR comes in. FAST, Healthcare Interoperable Resources, is the latest standard for representing healthcare data from HL7. It has a number of benefits, but the one we're interested in here today is that it splits the patient record into a number of discrete units called resources. Practically, this means that all allergies are in one type of resource while medications are in another. If we know how to ask using especially formatted questions, FHIR APIs can give us back just the pieces of information we want. This is exactly the sort of granularity we want to give to our vector index. Now we need to consider how to best provide that data to the embedder to get the best numeric representation in the index. FHIR is formatted in a standard called JSON. This makes it very easy for computers to read. The problem is that embedders are trained not on JSON, but on free-form text. This means that when we give FHIR to the embedder, the resulting numeric vectors are not very useful. However, we can transform the FHIR into pseudotext by flattening it into something that looks like sentences to the embedder. This gives us much better results in the index. There is one more thing we need to consider. Each FHIR resource is dedicated to its own type of data, and it's only linked to other resources for context. For example, an observation resource, which is where you would find blood pressure readings, has the systolic and diastolic numbers in it, but it only has a link to the patient. We need to include things like the patient's name in the pseudotext if we want the embedder to know about it. If we don't, questions about a patient will not find the right data. By adding some text to the entry before sending it to the embedder, we can make it easier not only to find the right data, but also that text will be available to the LLM and help it as well. The patient's name is an obvious one, but we might also include the patient's birth date and gender and other information. Now let's see all of this in action. You can read more about this and see some code examples in my article on Medium. Thank you very much. Please feel free to subscribe to my channel for more content about technology and healthcare. Also, please remember to leave a like and a comment if you found this video useful.